Let me begin today by reminding you of the ground we have covered in the first two lectures. By 1930, the physicists believed that all matter in the universe was composed of three particles: electrons, protons, and neutrons. He also believed that all energy, whether it existed as heat or light or chemical force, is basically electrical in character and manifests itself in discrete chunks, in discrete quanta. These quanta were called photons by Planck and Einstein. All matter and all energy in this view was then composed of just four fundamental entities: photons, electrons, protons, and neutrons. The electrons and protons carry an electrical charge. When accelerating, these particles emit heat or light in the form of photons. The neutron, however, is electrically neutral. Now, these four particles are not just simple chunks of matter or energy. One other property they all seem to possess is that of intrinsic spin. An electron or a proton continually spins like a top around an axis fixed in the body. And as I said in the second lecture, the spin motion, like all spin motions in the universe, is a half-integer multiple of the fundamental unit of Planck. Now, why should elementary particles behave like spinning tops? What gives them their intrinsic spin? Why should the spin values be just what they are? The answer to this last question was brilliantly given in 1928 by Dirac at Cambridge in a paper which is an epic of modern physics. In the second lecture, I spoke of the laws of persistence of inertia, of persistence of the spin motion. You may remember I said one could show that this quality of persistence in spinning, for example, was related to a symmetry of the universe, to a symmetry in respect of rotations. Dirac was able to show that when one marries together this notion of rotation symmetry of the universe with the ideas of Einstein's relativity theory, one can show that the electrons or the protons or the neutrons must indeed spin, and with the precise values which had been found by the experiment. As I said earlier, Dirac's work is one of the most momentous in modern physical theory. I hope you will bear with me for thus rhapsodizing about it without giving you the successive stages of his reasoning. It's impossible in a lecture of this type to convey the depth or the beauty of Dirac's work. Not only did he give a deeper meaning to the concept of intrinsic spin, Dirac was also able to deduce from the same equation something even more important. Dirac could show on general grounds that all particles in nature must exist in pairs, that to every particle there must correspond an antiparticle of precisely the same mass, the same spin, but opposite charge. Thus, the existence of the negatively charged electron must imply the possible existence of an anti-electron carrying a positive electric charge. If the hydrogen atom exists, there can equally well exist atoms of anti-hydrogen, perhaps in some distant corner of the universe. I have said in some distant corner of the universe advisedly, for Dirac could show that if a particle and an antiparticle collide, both of them must disappear. Their energy, their momentum, their spin going into photons. In Dirac's language, antimatter is minus matter, negative matter. Matter and antimatter just cannot coexist in the same part of the universe without the ever-impending catastrophe of annihilation. I must say, however, that some astronomers do believe that just this type of annihilation is taking place at certain sites in space far away from us, where one can locate powerful X-ray sources in the heavens. Dirac made his prediction regarding the existence of antimatter in 1934. The anti-electron was discovered in cosmic rays the same year. The discovery of the antiproton and the antineutron had to wait longer, till the completion of the giant proton synchrotron, the proton accelerating machine, in Berkeley, California, in the 1950s. At one stroke, Dirac had doubled the number of elementary particles from 4 to the number 8. There is an apocryphal story in Cambridge of how Dirac first conceived of the idea of anti or minus matter. As a graduate student, Dirac once attended a problems drive organized by the Cambridge Undergraduate Mathematical Society, the so-called Archimedeans. One of the problems presented to Dirac was the following. On a stormy night, 3 fishermen go fishing and make a big haul of fish. But the storm forces them to seek refuge on a lonely island where they tie up their boats and go to sleep. During the night, one of the fishermen gets up. He would like to get away. Without waking up his friends, he decides to divide the catch into 3 equal parts. He does this, but he finds that one fish is outstanding. This fish he throws into the sea, takes away his 1/3, and goes away. A short while later, the second fisherman wakes up. He does not know that one of his friends has departed. He also proceeds to divide the haul into 3 equal parts. He also finds one fish outstanding. He throws it into the sea and rows away with his 1/3 portion. The same thing happens a third time. The problem is, what is the minimum number of fish which can be subdivided in this manner 3 times successively with one fish outstanding each time? The story goes on that Dirac, when presented with this problem, thought for a few seconds and then jotted down his answer: -2 fish. You see, if you divide -2 fish into 3 equal heaps, each heap will consist of -1 fish with +1 fish outstanding. -3 + 1 equals -2. Now throw the outstanding +1 fish into the sea. Take your -1 fish away. Since -1 and +1 equals 0, you've really taken nothing out of the heap. You are leaving behind exactly -2 fish in the heap, which are ready for exactly the same subdivision by the second fisherman as before. At that time, Dirac did not worry what minus fish may signify, nor does the story relate if he got that prize that night. But when faced with the minus electrons 2 years later, as a consequence of his relativistic equation, Dirac just had to find a meaning for these minus particles. And he came up with the brilliant notion that these signified antiparticles, uncovering at the same time one more profound symmetry in the universe, the symmetry of matter and antimatter. Now, before we go any further, let me recapitulate once again the position that we have reached. In the 1930s, the view of nature was that all matter and all energy could be considered to be made up of 4 elementary particles, or of their antiparticles. Every particle possesses a specified magnitude of spin. It looks like a spinning top. In addition to the spin motion, electrons and protons carry an electrical charge, while the neutron is electrically neutral. Immediately after the discovery of the neutron, the question arose, if this particle is indeed electrically neutral, it can possess no electrical force of attraction or repulsion relative to protons or electrons. We had earlier learned in the first lecture that neutrons and protons together make up the central core, the central nucleus of all atoms. What then is the force which keeps the nucleus bound together? Why do the protons and the neutrons inside a nucleus not fly apart? The dilemma appears deeper still when one reflects that a nucleus is incomparably more compact, more tightly bound than any atom that we know of. To compare sizes, if a hydrogen atom is blown over to the size of the city of Karachi, the hydrogen nucleus would be no more than the size of the Qaid-e-Azam's mausoleum. This compactness, this tight binding, must come from some force inside the nucleus. We may call such a force the nuclear force, and this force must be at least 100 to 1,000 times stronger than the electrical force which keeps an atom together. The neutron, though electrically neutral, must carry a nuclear charge, and so indeed must the proton, since a nucleus contains protons also. The tremendous strength of the nuclear force compared to the electrical force would explain why a nuclear bomb, size for size, must be thousands of times more potent than a chemical bomb. This strength must explain why nuclear fuel in a nuclear reactor must deliver 1,000 times more power. With the knowledge of the nuclear force, of its immense strength, and with the knowledge of nuclear reactions, one knew that at long last one had found the reason which made the stars shine, and how the sun can pour out such vast amounts of energy without being depleted. I always fondly recall the story of Professor Bethe, the night that he first realized that the tremendous outpouring of luminous energy from the stars was basically the energy of nuclear reactions continually taking place in the star's interior. Bethe and his wife were standing gazing on the desert sky when Mrs. Bethe said, "How beautiful do the stars shine tonight." Bethe turned slowly to her and said, "Would you believe it? But right now you are next to the only person in the universe who knows what does make them shine at all. I have spoken of the nuclear force qualitatively so far. Since 1935, the major problem in physics has been to find its quantitative aspects. And I shall devote the remainder of this and the next lecture to these quantitative